section 2.5, the chain rule. So theorem, the chain rule. Let G be differentiable at X and let F be differentiable at G of X. Then F composed with G, well, the derivative, let's say it this way. The derivative of F composed with G is just the derivative of F. Oh, I should say it the other way. The derivative of the quantity F composed with G is equal to the derivative of F composed with G times the derivative of G. The derivative of a function is the derivative of the outside evaluated at the inside times the derivative of the inside. It actually looks nicer. I actually like it when I write it in Leibniz notation. So in Leibniz notation, it says that dy over dx is dy over du times du over dx. It looks like I'm just canceling the du's. Of course you're not. I mean, this is the actual theorem. So here's the theorem. But in this notation, it looks like you're just canceling out the du's, which will actually be very helpful, especially when you write the chain rule in differing situations, such as multiple variables. And so I actually prefer writing the chain rule in Leibniz notation. But don't be tempted to think that really what you're doing is canceling, because you're not canceling. Obviously, if you look at the way it's written here, there's no cancellation going on. There's no, and so it's very obvious from this sort of functional notation that, you know, I'm not doing any sort of weird cancellation or anything. It turns out that the proof of the chain rule is actually quite difficult using, oh, I guess, why is it difficult? Okay, so suppose you wanted to prove the chain rule using, well, the difference quotient definition. So if you did that, you'd say, well, the limit derivative so you take f composed with g, take the derivative of that. So that's a limit as h approaches 0 of f composed with g at x plus h minus f composed with g of x, all divided by h. Okay, so, well, if you rewrote this, you say the limit is h goes to 0 of f of g of x plus h minus f g of x over h. Well, I want here the derivative of g. So you'd say, okay, well, it's got to be, oops, g of x plus h minus g of x. And you'd have to do the same thing here, g of x plus h minus g of x. And you'd sort of say, well, this approaches g prime, and this approaches f of g prime of g of x. All nice and fine, except it's completely wrong because you could be dividing by 0. So the problem is that you could be dividing by 0. So you have to do much more subtle things to be sure that you're not dividing by 0 here. So rather than do that, let's not use the difference quotient definition. And so if I use, well, Lewis and Steinberg's definition for the derivative, things actually are a little bit easier. So since g is differentiable at x, then g of x, there exists some function, g prime of x, such that g of x plus h is equal to g of x plus g prime at x times h plus little o of h. Next, since f is differentiable at g of x, I'll call g of x y in this notation, just so that it looks a little nicer. And so when I write this, I'll just say, let this g here be y. Then I have that there exists some f prime of y such that f of y plus h is equal to f of y plus f prime of y times h plus little o of h. Okay, all nice and fine. Now, let me just collect everything together. So let's look at f composed with g at x plus h. Well, by the pointwise definition of composition, we have that this is f evaluated at g of x plus h. Well, what is g of x plus h? Well, g of x plus h is g of x plus g prime of x times h plus little o of h. And I'll replace my g of x plus h by that. So this is equal to f evaluated at g of x plus g prime at x times h plus little o of h. Let me rewrite this as, let's factor out an h. So this is equal to f evaluated at g of x plus g prime of x plus little o of h over h, all quantity, times h. And so I have here, well, this. And so let's use this fact. So I have that f of y is f of y plus h is just f of y. And so this is equal to f of g of at x plus this, which is f prime at g of x times this little h, which I'm calling this. So plus, oh, and I guess I called it this. Why did I write it that way? I guess I should have written, so plus this term. And so plus f prime at g of x times this little term here, which is g prime of x times h plus little o of h, plus little o of this guy. Well, this oh, that's why I wrote it this way. Little o of this. Well, this is bounded. I know that this doesn't depend on h. And as h approaches 0, this approaches 0. So this is here some constant times h. Therefore, as h approaches 0, this whole thing here, as h approaches 0, if you divide, you get just a little o of h. So this is a little o of h. Okay. And so let me simplify this. So let's multiply this inside the parentheses. And so I have that this is equal to f of g, f evaluated at g of x, plus, well, this term, f prime evaluated at g of x, times g prime of x times h, plus, well, this times little o of h is little o of h, plus another little o of h is little o of h. So I've shown that this is equal to f composed with g at x plus f prime composed with g at x times g prime at x times h plus the little of h. And so here's my derivative. Therefore, so here's my derivative of this. Therefore, f composed therefore the derivative of the quantity f composed with g is equal to the derivative of f composed with g times the derivative of g. It's equal to the derivative of the outer evaluated at the inner times the derivative of the inner. So let's do some examples. On page 158, in problems 1 through 6, write the composite function in the form f composed with g at x, identify the inner function u equals g of x, and the outer function y equal f of u, then find the derivative dy over dx. Okay, so let's do that. Now, of course, you could always do a trivial sort of function so that you did it as so you could always say, well, this is the composition of two functions, you know, y equals a sine of the cotangent of u, where u is equal to x. So you could always do something like that, but don't do that. So yes, that is the composition of, you know, you could just substitute in for ux and it gives you the original function, but we don't want to do that because that's not going to help us to take the derivative. What you want is the following. Let u equal cotangent x. Then y is equal to the sine of u. Therefore, using Leibniz notation, dy over dx is equal to dy over dx. And I can just, quote unquote, multiply and divide by du. Of course, I'm not multiplying and dividing by du. I'm using Leibniz notation. So this is using Leibniz notation. We have the following. So let's take the derivative of sine of u. So the derivative of sine of u is, well, cosine of u. Derivative of sine is cosine. Times du dx. So let's take the derivative of cotangent x. Well, the derivative of cotangent is negative cosecant cotangent. cosecant x, cotangent x. Now, one problem here is that this is in terms of u's and x's. I don't have a u in the original problem, so I can't just write this derivative, the dy over dx, where I have some other variable. So I have to plug in what u is. Well, and so this is equal to minus cosine of u, cotangent x, times everything else, cosecant x, cotangent x. And that is my derivative. Oh, I guess I should actually say this, that I've used the following fact, that dy over du is cosine u, and that du over dx was minus cosecant. Yeah, that's a cotangent. Minus cosecant x, cotangent x. So I use those facts, and of course the fact that u was equal to cotangent x to take the derivative. Of course, I have a bad habit of doing everything together, because after you have done these a few times, you do everything together. So any questions about that? I should have written this down first and then written this down. Okay, so let me do problem 7 through 46. Find the derivative of the function. Problem 10. G of x is equal to 2 minus sine x to the 3/2. So I'm going to use the chain rule, but there is something called the general power rule, which is the chain rule for a particular function, for the fact that your outer function is just a power function. So the general power rule which is just, again, a consequence of it's a corollary from the chain rule, which says that the derivative of some function to the power n is equal to n times f of x to the power n minus 1 times the derivative of f. So again, this is just the chain rule. The derivative of a function is a derivative of the outer, evaluate the inner, times the derivative of the inner. And so this is just the chain rule for a particular case that my outside function is this power function. Okay, so let's use this. So the derivative of any function is just going to be the derivative of the outer. Well, you notice that this is raised to the power 3/2. So let's bring this exponent out front. Times, well, rewrite what's on the inside. So let's rewrite what's on the inside, 2 minus sine x, to the power of 1 less. And so 3/2 minus 1 is just 1/2. times the derivative of what's inside. So now let's just take the derivative of what's inside. Well, the derivative of 2 is 0. The derivative of sine x is cosine x. So this is equal to minus, cosine x. And that's your answer. Any questions about that? Let me do problem number 18. So now I'm going to combine several rules. So to take the derivative of this, I have to use the product rule, Leibniz rule. So I'll take the derivative of the first times the second plus the first times the derivative of the second. So take the derivative of the first. Well, bring down the exponent out front. Evaluated at where I've subtracted 1 from the exponent times the derivative of what's inside. So this is the derivative of the first times the second. Plus, so I have done the derivative of the first times the second. Now I have to do the first times the derivative of the second. Plus the first times the derivative of the second. And so to take the derivative of the second here, I'll take the exponent, bring it out in front. I don't like putting it here. So I should put it out in front here. Times, well, let's rewrite what's in the inside to the exponent of 1 less, times the derivative of what's inside. So now let's take the derivative of what's inside. Derivative of x squared is 2x. Derivative of 2 is 0. And so this is times 2x. And you're done. So this is derivative of the first times the second plus the first times the derivative of the second. Any questions about that? Okay. Problem number 22. Y equals x plus 1 over x all to the power 5. Let me write 1 over x as x to the negative 1 so that I can use the power rule on it. So let's use first the general power rule. Bring down the exponent out in front. Rewrite what's inside to the power of 1 less times the derivative of what's inside. Derivative of x is 1. Derivative of x to the negative 1 is a negative x to the negative 2. You bring down the exponent of negative 1 out in front and then subtract 1 from the exponent to get negative 1. And that's your answer. Any questions about that? Oops. Any questions? Okay. Let me do problem number 46. So let's take the derivative of y equal x. So we're raising to the power 4, x plus, we're raising to the power 3, x plus, and we're squaring sine x. So we have several chain rules that we're going to use. In this case, actually, there are general power rules. So we're going to use the fact that all of this is raised to the power of 4. That's a general power rule. And then the fact that this is raised to the power 3, another general power rule. The fact that this is raised to the power 2. Remember that this exponent line here means that this is a exponent of that whole function. So this is the power rule. So the general power rule. So let's do this. Ooh, sorry. And so this is equal to, bring down the exponent out in front, 4. Rewrite what's in the parentheses, what's inside, x plus sine squared x cubed. All to the power of 1 less. So that's the derivative of the outer function. Bring the exponent out in front. Rewrite what's inside, all to the power of 1 less. Times the derivative of what's inside. So now let's take the derivative of what's inside. So derivative of x is 1 plus. Now I have to take the derivative of this. Well, this whole thing is raised to the power 3. So again, I have to use the general power rule. We'll bring the exponent out in front. Rewrite what's inside to the power of 1 less. And so I'll bring the 3 out in front. Rewrite what's in the parentheses. All to the power of 1 less. Times, it's the general power rule, times the derivative of what's inside. So let's take the derivative of what's inside. And so derivative of x is 1 plus, oops, here it is, plus, I take derivative of this guy. Well, notice that this is the sine of x squared. So again, I'm going to use the general power rule. We'll bring the 2 out in front, rewrite what's inside to the power of 1 less. And so plus 2 sine of x to the first times the derivative of what's inside. The derivative of sine x is cosine x. And I am done. Okay, so let me go over this again, because it's probably, there are a lot of the problem is that there's some insides. So there's an inside here, there's an inside here, and there's an inside here. So let's take the derivative of this function. So I take exponent, bring it out in front, rewrite what's inside. So I brought the exponent out in front and rewrote what's inside. Times, now I have to take the derivative of what's inside. So this whole quantity here is the derivative of what's inside. So this is what the derivative of what's inside. So now let's only look at this guy. So it's going to be 1, derivative of x is 1, plus the derivative of this. So it's 1 plus the derivative of this guy. So now the derivative of this is that. So derivative of x plus sine squared x, all quantity cubed, is going to be this thing. So how do I do that? Well, again, General power rule. Bring the 3 out in front, rewrite what's inside, all to the power of 1 less. So bring the 3 out in front, rewrite what's inside to the power of 1 less, times the derivative of what's inside. So now this is the derivative of this guy. So this thing here is derivative of this inside. Well, the derivative of x is 1. Derivative of this, sine squared. Well, again, you have an inside. And so this is sine of x to the power 2. So bring your exponent out in front. Rewrite this. That's the power of 1. It really doesn't. Maybe I'll get rid of that so that it looks confusing there. That almost looked like a prime. So to the power 1 times the derivative of what's inside. So the derivative of what's inside is cosine. So this is the derivative of this term, derivative of this guy. So that's what this is. So to take the derivative of this guy, you just take the derivative of the outside function, which is this, evaluate the inside function, which is this, times the derivative of the inside function, which is this guy. To take the derivative of this inside function, well, this was easy. But this, I'm going to have to use the general power rule. And so you take the exponent, bring it out in front, rewrite what's inside, all to the power of 1 less, times the derivative of what's inside. So this is the derivative of what's inside. Again, derivative of x is easy, that's 1. Now I have this guy. So to take the derivative of this guy, I bring the exponent out in front, rewrite what's inside, times the derivative of what's inside. And now you are done. I've done all the insides. So notice I had this inside, I then had this inside, and then I had this inside. And I've taken all those, the derivatives of each of those insides. Okay, any questions about that? I know that when we have these nested sort of chain rules, students, when you look at students, their eyes glass over and they just sort of look like they're not there. Any questions about this? Any questions about this? Okay, so I'm going to assume that there's no questions. Let me do in problems 47 through 50, find the first and second derivatives. Problem 48. Y equals 1 over 1 plus the tangent of x, all quantity squared. Well, I could just use the quotient rule for this and it'll take a while. But rather than using the quotient rule, I'm going to rewrite this. I'm going to simplify this, make my life easy. And so I'll write this as 1 plus tangent x, all to the power of -2. And let's use, well, the general power rule. So the derivative, bring down the exponent out front, rewrite what's inside the parentheses, all to the power of 1 less, times the derivative of what's inside. Derivative of 1 is 0, derivative of tangent x is secant squared x. Let's take the second derivative. So I'm going to have to use the product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. So let's do that. So let's take the derivative of the first function. I'm going to bring the exponent out in front, rewrite what's inside to the power of 1 less. Well, -2 2 times negative 3 is a positive 6. Rewrite what's in the parentheses. Sorry, okay, why do you do that? Rewrite what's in the parentheses. 1 plus tangent x. All to the power of 1 less. Negative 3 minus 1 is negative 4. Times the derivative of what's inside. Derivative of 1 is 0. Derivative of tangent of x is secant squared x. Times the second. Well, that's another secant squared x. Plus the first, negative 2, 1 plus tangent x. Negative 3. So that's the first, times the second. Well, to find the derivative of the second, I have, well, secant of x, and I'm squaring it. And so I'm going to bring the exponent out in front, rewrite what's inside to the power of 1 less, times the derivative of what's inside. And so let's bring the exponent out in front, 2. Rewrite what's inside, secant x, all to the power of 1 less, well, 2 minus 1 is 1, times the derivative of what's inside. Derivative of secant x is secant x tangent x. And you are done. Any questions about this?
Could you run through the middle of that one? Like,
Sure. Okay, so let me run through this. So, to find the derivative, I'll take the derivative first. So I'll bring down the exponent out in front. Negative 3 times negative 2 is positive 6. Rewrite what's inside, all to the power of 1 less, times the derivative of what's inside. Derivative of 1 plus tangent x is secant squared. So this is the derivative of the first times the second, plus the first times the derivative of the second. So now let's take the derivative of secant squared. Just recall that this means secant of x quantity squared. So I'm going to bring the exponent out in front, subtract, rewrite what's inside to the power of 1 less. So I'll bring the exponent here out in front, rewrite what's inside to the power of 1 less, times the derivative of what's inside. Derivative of secant x is secant x tangent x. Is that clear now?
yeah.
So it's the derivative of the first times the second plus the first times the derivative of the second. Yeah, the first time you see these, once you have multiple chain rules, it's always a little bit complicated for students. Okay. Let me do problems 51 through 54. Find an equation of the tangent line to the curve at the given point. Problem 54. Y equals sine squared x cosine x at the point pi over 2, 0. So the first thing is to find the slope of the tangent line. Let's take the derivative. I'm going to have to use the product rule. So I'm going to have to use the product rule here. And to take the derivative of this, I'm going to have to use the general power rule. So the derivative of the first, derivative of sine squared x, is, bring the exponent out in front, rewrite what's inside the parentheses, all to the power of 1 less. Oh, when I keep saying here to take the, to rewrite what's inside the parentheses, even though I don't write a parentheses here, it's assumed there is a parentheses in this notation. So that's what I mean by here. I'll rewrite what's inside the parentheses. So rewrite what's inside the parentheses to 1 less times the derivative of what's inside the parentheses. Well, the derivative of sine x is cosine x. Plus a second. And so that's the, oops, times the second. Yeah, so that's, where's the second? There. No, come on. Times the second. Okay, so the derivative of the first times the second plus the first times the derivative of the second. The derivative of cosine x is a minus sine x. And so that's why I wrote this as a minus. It's supposed to be plus, but the derivative of cosine x is minus sine x. So now let's evaluate when x is pi over 2. So the slope is equal to y prime at pi over 2, which is 2 sine of pi over 2. Cosine times cosine is cosine squared at pi over 2 minus sine squared at pi over 2. Oh, sine cubed times sine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. And we're squaring that. Sine of pi over 2 is 1. Sine of pi over 2 is 1. And so this is just equal to -1. So again, let's use the point slope form for the equation of a line. Oh, and I guess in high school, they do, I guess the way they do it is they always use the slope-intercept form. Why? Usually because that involves the most fractions in algebra. Usually it involves the most fractions. So because of that, they use that so that students get additional practice on fractions. I don't need practice on fractions, so I'm going to use the point slope form for the equation of a line. So y minus y1 equals m x minus x1. So we're doing this at the point pi over 2, 0. So y minus 0 equals m, -1, x minus pi over 2.